I'm Dr. CS, and this is the relational model. The heart of the relational model is the relation schema. In its simplest form, a relation schema is a name, R, and a list of attributes, A sub 1 through A sub n. Each attribute has a domain you can think of as a set, like a data type, and a name, and the name indicates the role played by the values in the tuples, the values that come from the domain of that attribute. For example, say we have an author relation schema with author ID, first name, and last name. Author ID would come from the domain of integers. First and last name would come from the domain of strings. And the roles that they play are indicated by the name. So author ID plays the role of a identifier, for example. A database schema is just a collection of related relation schemas. For example, if you had a pubs database, you would have relation schemas for things like book, author, and pub for publication. A relation or relation state is a set of tuples that conform to a relation schema. So, for example, given the author relation schema, with author ID, first name, and last name, a particular relation conforming to that schema might be such as the table listed here with these four authors. And a database is a set of relations. Just like a database schema is a set of related relation schemas, a database is a set of relations conforming to those schemas. A tuple is an ordered list of values. For example, if you have T sub 1 is a 3-tuple containing the values 1, John, and McCarthy, that would be a tuple that conforms to the author schema with author ID, first name, and last name. Note that the order is important here. So the attributes are in a particular order, and the values in a tuple have to conform to that order. You can refer to the individual elements of a tuple with 3 different notations. The most common one is bracket notation, so T sub 1 first name with first name in brackets, which is similar to using hash tables in many programming languages. And then there's an object notation, T1.firstName, and a positional notation, T1.2, indicating the second element of the tuple. Note here that the indexes in a tuple start from 1, not 0. So T1.2 is the second element of the tuple, John in this case. And the degree or arity of a relation schema is the number of attributes that it has. So author has degree 3. So as we said, each attribute has a name and a domain. And the domain is a set of atomic values that a tuple can have for that attribute. And this domain is the logical definition, such as integer or string. But an attribute can also have a format. For example, in the relation that we see here, home phone could have a format DDD-DDDD, where D is a digit. This example here shows us a relation conforming to a relation schema student that has these 7 attributes in the header row here. And then each one of these rows is a tuple in that relation. The mathematical definition of a relation is quite simple. Given a relation schema R A sub 1 through A sub n, a particular relation conforming to that schema is a subset of the cross product of all the domains. Remember, the domains are sets, so if you had finite sets, you could literally just list them all out, and we'll do that in just a minute. So the total number of values, or cardinality of a domain D, is vertical bar D vertical bar in the usual set notation. So the maximum number of tuples you could possibly have in any relation schema or any relation conforming to schema R is the magnitude or cardinality of the domains multiplied together. Let's look at an example. Let's say we have a relation schema R with attributes A sub 1 and A sub 2, And the domain of A sub 1 is the finite set containing 1 and 2. And the domain of A sub 2 is the finite set containing A and B. What are all the possible tuples that could appear in any relation conforming to schema R? Well, all we have to do is take the cross product of these two domains. So it's 1 in A, 1 in B, 2 in A, and 2 in B. And so given the definition of a relation state, what would be the maximum size of any relation conforming to schema R? It would be 4. Because a relation, remember, is a set of tuples, which means that you can't have any duplicate tuples in a relation. Relations, the values in relations must be atomic. This is sometimes called the first normal form assumption. We'll learn about normal forms quite a bit later. Attribute values in tuples have to be indivisible, so you can't have any compound or multi-valued attributes like you do in entity relationship models. You have to break those up and represent them differently in a relational database management system. You can have nulls for some tuples for some attributes, not all attributes. We'll see that later. And if we look at this example here, we've added middle name to our author table. And if we look at the first tuple, notice that we don't have a middle name for John McCarthy. It's just null. Now, what a null means in a database is not clear from just the information in the database. It could mean that we don't know the first name. It could mean that John McCarthy doesn't have a first name, or that it's not applicable in our domain. So because of the problems associated with nulls, and there are many other problems as well that we'll learn later, we try to avoid nulls as much as possible. And then finally, the closed world assumption, which is that facts that are not asserted explicitly in our database are assumed to be false. So for example, given this author table, if this is the complete author table, and we ask if J.K. Rowling is an author, the answer would be no. And the reason for that is that in a database application, when you answer questions about your data, you answer those questions based only on the data you have in your database, nothing else. A superkey is a set of attributes of a relation schema that uniquely identifies each tuple in the relation. So if you have two different tuples, the values of their superkey attributes will be different. They must be different. So by the definition of the relational model, the full attribute set of a relation schema is a so-called default superkey. So pause for a moment and make sure you understand that last statement. By the definition of the relational model, the full attribute set of a relation schema is a default superkey. A minimal superkey, or just a key, is a superkey where if you removed an attribute, it would no longer be a superkey. It would no longer uniquely identify a tuple within a relation. So let's look at the example of author with author ID, first name, and last name. So we know that the full attribute set is a default superkey. Now, if we took out last name, would author ID and first name together uniquely identify a tuple within an author relation? Yes, it would. And so that means that author ID, first name, and last name together are not a superkey, because if we take last name out, what's left is still a superkey. Now, if we continue, if we take first name out and we're left only with author ID, does author ID by itself uniquely identify every tuple? The answer is yes, and that makes author ID a minimal superkey, or just a key. And in general, relation schemas can have multiple keys, and we call all these keys candidate keys, and we choose one of them arbitrarily to be the primary key. And once we do that, we underline it in relation schemas. So author ID here is underlined. It's the primary key. One of the most important features of the relational model is that you can represent database integrity constraints. We've already talked about inherent model-based or implicit constraints, such as the domain constraints that attribute values have to be in the domain for that attribute and conform to any formats that may be defined, and that those values and tuples have to be atomic, indivisible. There are also schema-based explicit constraints, such as key constraints that no two tuples can have the same values for the primary key. Entity integrity constraints, which means that no tuple can have a null value for any part of the primary key. Remember, in general, primary keys can be a single attribute or they can be a combination of attributes. And no part of the primary key can be null. And then referential integrity constraints, which occur when tuples in one relation reference tuples in another relation. And we'll say a lot more about that in just a few minutes. And then finally, you have application-based constraints. These are also called semantic constraints or business rules. And these are constraints on attribute values that cannot be expressed in the relational model directly. So, referential integrity constraints occur when you have a foreign key value from a tuple in one relation referring to the key of a tuple in another relation. All right, so formally, if you have two relation schemas, say R sub 1 and R sub 2, we'll say that R sub 1 is referencing R sub 2. So R sub 1 is a child relation, R sub 2 is a parent relation. If R sub 1 has a set of attributes we call the foreign key, or FK, then the attributes FK in R1 have to have the same domain as the primary key in R2, the parent relation, and for any tuple in R sub 1 that references some tuple in R sub 2, either the foreign key in T sub 1 has to have the same value as the primary key in the tuple it references in the parent relation, or the foreign key in the referencing relation has to be null. And we'll see some examples of those in just a minute. So let's see how we could diagram these foreign key relationships, and this will make things quite a bit clearer. So we'll just look at employee and department here. So if we look at the employee schema, we see that the social security number is the primary key, and for department, D number is the primary key. Now notice that department also has a manager social security number attribute, and it points to the employee relation. Now, it doesn't have to point directly at social security number because by the definition of foreign keys, if you have a foreign key referencing another relation, it references the primary key. And the primary key of employee is social security number. But we typically have it point at the primary key anyway. So that means that manager social security number in department has to be null, meaning that the department does not have a manager, or it has to have a value that is present in the relation for employee as a social security number, right? So it has to reference a particular employee. It can't reference an employee that doesn't exist. All right? Notice also that we can have a recursive foreign key relationship. So for an employee, notice that there's a supervisor social security number, and it references employee. So it references social security number. So every employee has a direct supervisor, and that's represented with a recursive foreign key relationship in the employee relation. Semantic integrity constraints are things that you can't specify in the data definition language of a relational database. Some databases include extra features such as triggers and assertions that will allow you to do semantic integrity constraints, but usually they're checked in application code like Python or whatever code is using the database as a backend data store. An example of this is you might have a business rule that the salary of an employee cannot exceed the salary of the employee supervisor. You might want to also add some additional constraints for things like the employee's start date can't be earlier than the employee's birth date, things that just sort of make sense, just sort of sanity checks on the data. And those are semantic constraints or business rules. So there are, whenever you insert data into a relation, update the data in a relation, or delete data from a relation, you risk committing a constraint violation. So, for example, when you put a tuple into a relation and it has an attribute value that's not in the attribute's domain, that's a domain constraint. If you try to put a tuple in a relation with a key, and that key is already in the relation, that's a key constraint. If you try to put data in a tuple and with a null value for some part of the primary key, that's an entity integrity constraint, and you can't do that. And then there are many ways to create referential integrity constraints. And we'll see examples of those right now. So domain integrity violations occur when you do things like if you inserted the tuple to Jenny McCarthy, where 2 is spelled TWO and it's a string, that string is not in the domain of author ID, and so that's not legal, right? Because the domain of author ID is integer. And then if you try to do a similar thing, updating 1 John McCarthy to 1 John 1, 1 is not in the domain for last name because last name is supposed to be a string. If you try to insert a tuple, such as this tuple, into the database, 1 already exists as a primary key, and so that's a key integrity violation, and it's not allowed. And then updating works the same. And then if you try to insert a null for any part of the primary key, null's not allowed for primary key. That's an entity integrity constraint. And then referential integrity violation examples are much more numerous. It's much easier to create a referential integrity violation. So here are a few examples. Say we have an author table or an author relation and a pub relation, pub for publications. And we're just going to say here, this isn't a perfect database schema design here, but we'll say that every publication has exactly 1 author. Of course, that's not true in general. We'll learn later how to model that in a relational database, but for our purposes here, this works. So we have the primary keys underlined for each table. And then we say that pub author ID is a foreign key to the author relation. So that means recursive functions of symbolic expressions in their computation by a machine has author ID 1, and that referenced the primary key of 1 in the author table, which means that John McCarthy is its author. Mathematical theory of communication is authored by author ID 4. 4 exists in this table. Of course, that's Claude Shannon's pretty amazing discovery for a master's thesis. And so on, right? So that's how foreign keys work. So if we try to update 1 John McCarthy in the author table to 2 John McCarthy, this would break the reference between this publication and the record John McCarthy. And so that would be a referential integrity violation. If we tried to delete 5 Alan Turing from, that should be from pub. This here should say, that should say author. So if we tried to delete 5 Alan Turing from the author relation, that would orphan computing machinery and intelligence from the pub table. So I'm getting ahead of myself. The pub relation. We're still talking about the relational model theory. All right. So that's a referential integrity violation. And then if we updated in the pub table the calculi of lambda conversion to this tuple, where we change the author ID reference from 6 to 7. 7 doesn't exist as a primary key in the author table, so that's a referential integrity violation. And then finally, we have something a little more subtle. So if we update 5, the calculi of lambda conversion, to have the author ID null, so that is technically not a referential integrity violation, but it does create bad data because it says that we have a publication without an author. And while that's not strictly speaking a referential integrity violation, it does create bad data, and we'll see how we can prevent that when we learn SQL. All of these things that I've mentioned here, there are ways to prevent those from happening in SQL, modern SQL databases. So the relational model is a mathematical database model, and it is the theoretical underpinning of relational databases. And aside from this rigorous grounding, one of the biggest strengths of the relational model is that it can model constraints, and in database management systems, enforce those constraints. So if you have a database application where the integrity of your data is very important, a relational database management system is the right tool.